Good morning. My name is Thomas Mueller. I'm the Director of Applications Development for the AFM business at Bruker, and I'd like to welcome you to this installment of the Bruker AFM webinar series. This presentation today is titled Measuring Nanoscale Viscoelastic Properties with AFM-based nano-DMA. It will be presented jointly by Dr. Dalia Yablon at Surface Car and Dr. Bede Pittenger at Bruker. Before I introduce Dalia and Bede, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar. If you have a question, please type it into the questions dialog box on your screen. We will accumulate these questions to the presentation, group them together, and then answer them at the end of the prepared remarks. Quite often we have more questions than we can answer in the session, and in those cases, we'll be sure to follow up by email. Also, if you would like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within 1 week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you'll also be receiving an email with this link. Finally, when you exit the webinar software, you'll be asked to take a brief survey. We'd very much appreciate if you take the time to complete this, as it helps us pick the topics that are most important to you and to generally make this series better. So let's get started, and let me introduce our two speakers today, Dalia and Bede. Our first presenter, Dr. Dalia Yablon, is the founder of Surface Car, an AFM and nano-notation-based measurement and consulting company in the greater Boston area since 2013. Previously, Dalia spent over a decade developing and leading scanning probe microscopy research at ExxonMobil Research and Engineering, and edited a book on SPM in industrial applications from Wiley Publishing. Dalia holds an A.B. in chemistry from Harvard University and a Ph.D. in physical chemistry from Columbia University. Our second presenter, Dr. Bede Pittenger, is a senior staff development scientist in the AFM unit of Bruker. He received his Ph.D. in physics from the University of Washington, Seattle in 2000, and has worked with scanning probe microscopes for 25 years, building systems, developing techniques, and studying properties of materials at the nanoscale. His work includes more than 30 publications and 3 patents on various SPM techniques and applications. His interests span topics from interfacial melting of ice to mechanobiology of cells and tissues to the nanomechanics of polymers and composites. So, let me turn it over to Dalia now to begin this presentation that is titled Measuring Nanoscale Viscoelastic Properties with AFM-based nano-DMA.
Thank you, Thomas. So we all know that AFM is excellent at measuring a variety of different properties on the surface, but it is especially primed to conduct nanomechanical measurements. And that's because we have an inherently mechanical interaction between our probe and sample. There are many ways that the probe can interact with the sample through both resonant and non-resonant techniques, and there are many observables that we can monitor. But in terms of conducting nanomechanical measurements, AFM faces different challenges for measuring properties on samples that are stiff, let's say 10 gigapascals or higher, as softer materials in the kilopascal to gigapascal range, and viscoelastic materials, materials that have a frequency dependence to their elastic properties. So for stiff materials, some of the challenges that AFM faces include sensitivity. The cantilevers are actually fairly soft and compliant, and we can only make them so stiff. So often we just run into a wall in terms of how sensitive this cantilever can be on a stiff sample, unless you go to higher order modes. Also for stiff and especially hard samples, AFM can suffer from probe wear. Now in soft materials, AFM faces different challenges. So now probe contamination can be a problem. A lot of soft materials can be fairly sticky, so adhesion is a challenge. And finally, limitations in contact mechanics models that are available to us to model the interactions between AFM tip and samples, they have limitations and they don't always work for all the samples all the materials that one might want to measure. Finally, for viscoelastic materials, AFM faces all the problems for soft materials, because most viscoelastic materials are soft. But now we also add a frequency problem, both for measuring the frequency. In other words, knowing what frequency is the sample experiencing during the AFM measurement, and then also matching the frequency. So AFM measurements happen at a certain frequency, and you might want to match the mechanical properties to other techniques that operate in a totally different frequency regime. So before we dive into all the techniques to measure these properties, let's just do a quick review of elastic and viscoelastic moduli. So we'll start off with the static elastic modulus, often very well known, called the Young's modulus. And the Young's modulus is simply a proportionality constant between the stress and strain of a material during elastic deformation. Now, the focus of today's webinar is on dynamic moduli. And these are moduli that are measured when you apply an oscillatory stress to the sample, as shown here on the right. And then you measure the resulting strain, as shown here under my cursor. And you can see that there is a phase shift between the strain and the stress. So the modulus is actually complex for viscoelastic materials, materials that have this time dependence to their material properties. And so there's both a real and imaginary part. The real part we refer to as a storage modulus. That is called either G prime or E prime, where this letter simply refers to how is that oscillation being applied. So G, it's in shear, and E, it's in tension. And it's simply equal to the initial stress over strain times the cosine of this lag, delta. The storage modulus is the elastic component of our response and refers to the energy stored per cycle in oscillation. And note that if this lag is 0, storage modulus simply goes to our static elastic modulus. Now, the loss modulus is termed either G prime or E double prime, and that's equal to the initial stress over strain times the sine of the lag. The loss modulus is the viscous component of the response and refers to the energy lost or dissipated per cycle. And note that it goes to 0 if this lag is 0. Now, the final viscoelastic property is called the loss tangent, and that's simply the loss modulus over the storage modulus, the ratio of the two. The loss tangent is probably the most empirically useful, especially in the polymer community. A tan delta is a synonym for loss tangent. And here you can see, again on the right, some plots of the storage modulus, the loss modulus, and loss tangent as a function of frequency and a function of temperature. And you can see the loss tangent, again, just being the ratio of the two. The reason we like that one is that there are peaks in the loss tangent when you collect it as a function of frequency and temperature. And those peaks pinpoint thermal and structural transitions in our material. So that's very useful information. On a practical level, what values loss tangent have are on the high end for softer, more fluid-like materials. Those will have a higher loss tangent. So for example, a rubber might have a loss tangent of approximately 1. Going down to a thermoplastic like high-density polyethylene, that material would have a loss tangent of about 0.1. And then as you go into the stiffer, harder, less dissipative materials, the loss tangent becomes vanishingly small. Now there's a final modulus called a reduced modulus, and the reduced modulus is actually the parameter that we always measure in AFM, and that's simply the combined tip and sample properties. So this is what we measure, and then we're able to extract out the sample modulus. Now in the bulk, we use dynamic mechanical analysis, or DMA, to measure viscoelastic moduli of solid samples. This is a very common tool in the polymer industry, and here's just an example of a DMA from TA Instruments. And again, it works by applying a sinusoidal stress and measuring the resulting strain. It does so as it varies temperature over a wide range, as well as varying frequency. I just want to point out what this frequency range is. So on the low end, I have 0.001 hertz, which is very low, very slow. DMA is not often done at this extreme low frequency because it is a very slow measurement to make. But note also what the upper end of the frequency range is. It's only 200 hertz, which in the realm of AFM measurements that were often operating in the kilohertz and sometimes even megahertz regime, 200 hertz is quite low. Also in DMA, you don't have to worry about adhesion, which you'll see will come up obviously in AFM. Now there are different ways to mount the sample and oscillate it in DMA, and here I just show two examples of the clamps. So our sample is maroon, and here it's being held in tension, and here it's being held in a 3-point bending clamp. The tension configuration is the best analog to the AFM tip sample interaction, but 3-point bending is very common as well. And here is just some data again from TA Instruments, looking at the various viscoelastic moduli, the storage modulus, loss modulus, and then loss tangent for pressure sensitive adhesive. So the current status of nanomechanical measurements with AFM affords us quite a few techniques to get at these properties or contrast. So force spectroscopy is a very well-known, widely used method to probe the elastic modulus. We also have phase imaging, which is an imaging method that derives its contrast based on a convolution of elastic and viscoelastic properties. A more recent method that's been developed for viscoelastic moduli is contact resonance. And here is an image, a contact resonance image, where the storage modulus, E prime, has been mapped on the surface of a multi-component polymer blend. There is also peak force Q&M to measure the elastic modulus. And so here is an image of a 3-component polymer blend measured with peak force Q&M. Now, the focus of today's webinar is a new method, a new addition to our capabilities, which is AFM-nDMA to measure viscoelastic moduli. Now, I said that in the bulk DMA, they don't have to worry about adhesion. It's macroscopic in the bulk, and that's very fortunate. Now, in the AFM world, which operates on the nanoscale, we do have to worry about adhesion because there is adhesion between tip-sample interaction, especially on a lot of the materials that one might want to probe viscoelastic properties because they do tend to be on the softer and stickier side. So there are two main contact mechanics models available to us to include adhesion in our tip-sample interaction. The first one is called DMT, and that accounts for adhesion outside the contact area in the blue areas shown here. You can see a force versus distance curve. This is what a DMT would look like. And then for samples that have more adhesion or stickier, we have JKR, which accounts for adhesion within the contact area shown here. This is applied here. And these are, again, both models that incorporate adhesion, unlike the Hertz model, which is our basic contact mechanics model, which does not account for any adhesion. So here's an example of an AFM method to measure these properties. So peak force Q&M, and it's using the DMT model, so adhesion just outside the contact, on this blend of polypropylene, polyethylene, polystyrene. And you can see we've compared the modulus measured by AFM, that's in red, with the DMA value and getting very nice accuracy with those. So all the nanomechanical methods that I mentioned face universal challenges. related to the fact that they're being measured with AFM. All these measurements require calibration of our spring constant and lever sensitivity. And so we can look at the formula for the modulus by the DMT model. The DMT model is basically the Hertz model with adhesion, and use a variance formula to estimate the error of different variables to this formula. And we can see that tip radius and cantilever spring constant are significant and do show up in this equation, and errors that we need to worry about. So fortunately, there have now been developed some new probes that address this particular area. The first component of these probes is that they have well-controlled tip radii. They come in two flavors, 30 nanometers or 125 nanometers as measured by the SEM. And you can see here the SEM images of these probes. And second, they come with spring constant calibrated by highly accurate laser Doppler vibrometer. This is far more accurate than the thermal tunes that many of us use to calculate spring constants. So this is a real improvement. Now, our lever sensitivity still does require calibration, and that is done through a static force curve on an infinitely stiff sample like a sapphire. It's a classic method. But there, at least this way, using these probes, we now do not require a reference sample for the other calibrations. So here is just a bit of a summary of the challenges with current AFM-based methods for nanomechanics. So here are the techniques that I mentioned: force curves, phase imaging, contact resonance, peak force, and then the new entry to this field, AFM-nDMA, that is a focus of today's webinar. And then down here I have bulk DMA, which is what we're ultimately comparing to. So if we look at the modulus that is measured, and then the frequency space, whether we have a linear or nonlinear probe sample interaction and what models are used, we can see the space that bulk DMA resides in. So very low frequency, a linear probe sample interaction, obviously no contact mechanics models, and then see how these other techniques line up and compare with these bulk DMA measurements that we're ultimately going to be comparing to. Okay, and now to Bede.
Thanks, Dalia. As Dalia mentioned, we at Bruker have been working for a while to improve the nanomechanical measurements with AFM. In the last couple of years, we've made significant progress in improving the system calibration through these probes. And we've also added contact resonance to allow measurement of storage and loss modulus at high frequencies. However, as Dalia pointed out, until recently, there are some important gaps between the needs of polymer rheologists and the capabilities of atomic force microscopy. The first one is really that rheologists need to measure the storage and loss modulus at multiple frequencies and multiple temperatures to completely characterize their polymer behavior. Additionally, they are accustomed to using the bulk DMA to analyze their samples. So direct comparison with the previous results that they've collected requires low frequencies. That's typically under 100 hertz. So we've been working with several different collaborators, and additionally our colleagues at Heisotron, which is now part of Bruker, to fill this gap and by developing a new mode for our dimension icon AFMs. And this mode is the AFM-nDMA that Dalia mentioned. So the first thing we recognized when we started working with these collaborators is that the low frequency needs of the rheologists are in conflict with the needs of imaging focused modes like peak force tapping and tapping mode. In imaging modes, you typically want to go as fast as possible and minimize the time in contact with the surface. This means that we're going to plunge in and rip out from the surface. So the tip is going to go in and out from the surface every cycle, making and breaking contact. And it makes inherently nonlinear measurement. Since it's not linear, the nominal frequency of the method, so say the frequency that you're working with peak force tapping or tapping mode, that would not be the actual interrogation frequency of the material. And in addition, the frequency itself doesn't fully define the state of the measurement, because you would need to include amplitude and set point as well to fully characterize that. In addition, tapping-based methods are resonant methods, so they add a couple of additional constraints. Firstly, you're limited by whatever the resonant frequency of the cantilever is, or in terms of contact resonance, it would be the frequency of the contact resonance. So you're not able to do a nice sweep in frequency like you might be able to with a non-resonant method. And secondly, the frequencies in tapping-based methods like phase and multi-frequency methods are typically about 100,000 times too high. So they're way off of what we'd really like to be able to use when we're comparing to a bulk DMA. And finally, depending on which kind of tapping-based method you're working with, you may have a hard time quantifying the load and adhesion. And you may also find that it's difficult to actually have a model which can calculate storage and loss modulus in the presence of adhesion. So in order to address these, we talked to our collaborators again, and we realized that we needed a different approach, one that provided a well-defined rheological frequencies as a perturbation of a carefully controlled preload. So we come into the surface, we preload the sample at a known force. Then we, once we're in contact, we modulate at a well-defined frequency, which would be also low amplitude, so we can be in the linear regime. We can control whatever frequency we like, so we can do a spectra if we want to. And then we retract, and we can fit that retract with a contact mechanics model that includes adhesion, for example, JKR, to obtain a contact radius, and that allows us to get our storage and loss modulus from the raw data. I will now describe the analysis of this type of data. If you are familiar with the literature, you may recognize this publication listed below here from Professor Nakajima, one of our collaborators in Japan. So essentially what we want to do here is we want to apply a sinusoidal motion to the Z piezo and measure the motion of the tip. And that will give us an amplitude ratio. So a ratio between the amplitude of the Z motion and a ratio of the and that of the deflection, and a phase shift between that Z piezo motion and the deflection signal. Once we've done that, we do some basic complex algebra, and we get a stiffness, which is just the force divided by the deformation of the material. If we separate out the real and imaginary parts, we get some real and imaginary stiffnesses, and we can take the ratio of these two stiffnesses to get the loss tangent directly. So this is implemented on the icon in two different modes. Firstly, we have mapping of the storage and loss modulus or loss tangent at a single frequency. And you can see here a map of the storage modulus of a polymer blend. This is at 100 hertz, so storage modulus at 100 hertz mapped out. But you can also go and choose separate locations on here, and we can do spectroscopy at user-selected points, and that gives us a series of measurements at different frequencies. So down below here you have a plot of the frequency for each of these circled areas, and we have storage modulus versus frequency for each one. So it takes about 15 minutes to collect a 48 by 48 point map like this at 100 hertz. But the individual spectra can take a bit longer, even up to several minutes at a single point. So a few minutes are needed, or a few tricks are needed to do this well. So here is some sample data. And essentially, the ramp script with nano-DMA has segments that allow for control of the preload, so going into contact, and then a segment where we just hold the force constant for relaxation, and then a bunch of different modulation segments, and then finally a retract segment where we can calculate the contact radius. Depending on what the frequency of these modulation segments is, we may either acquire the raw deflection, which allows us to do better filtering and creep correction, or we might use a lock-in based demodulation if the frequency is high enough. To get to the moduli, like the storage and loss modulus, we also need a contact mechanics model like JKR to estimate our contact radius. This is the conversion between this complex, or the real stiffness, and the storage modulus. So we just divide by 2 times the contact radius, and the same is true for the loss modulus. But we need to track that, and there's an intrinsic difficulty in making these viscoelastic measurements accurately when you're talking about doing indentation at these time scales. The issue is that the samples that exhibit a significant viscoelastic response also exhibit relaxation under load. And this relaxation leads to changes in the contact radius during the measurement. So really we want to be able to know what the contact radius is at every frequency in order to get the storage modulus at every frequency. But thankfully, our friends at Hysotron also work with indentation of viscoelastic materials, and they've helped us to develop some strategies to solve these issues with creep at long time scales. So what we do is we add reference segments all with the same frequency throughout the measurement, and one right before the retract. We measure the contact radius during the retract using the JKR model, and then we can use these reference segments to correct the contact radius at earlier times by interpolating between them. So here is a plot of contact radius versus time in one of the measurements. Now these scripts have a lot of segments. We want to be able to go to multiple different frequencies, so it's a bit tedious to set up the scripts for spectroscopy. So we developed a specialized ramp script generator for use with AFM-nDMA. And in most cases, you'll be able to just select what range of frequencies you want to work with and how many steps, and choose a preload. This is similar to the DMA parameters that you'd have if you were working with a bulk DMA machine. However, if you work with atomic force microscopy, you may want to be able to adjust some other parameters. For example, exactly how you want to distribute your frequencies in the script, whether you want to shuffle them, whether you want to how many reference segments you'd like, how much relaxation you'd like, how big of an approach you need, things like that. So all kinds of ramp parameters. So we do have advanced parameters if you need them. They can be adjusted in the ramp script generator. And then you can also, once you've generated the ramp script, you can load it into the general ramp scripting interface and use that to modify it. That gives you more flexibility, but it is, as I mentioned, a bit tedious when you start working with long scripts. For variable temperature measurements, a new low drift heater has been developed to optimize the accuracy of collocation of the spectra and the images, and also to reduce the time required to stabilize the system when changing temperature. So this is our low drift heater on the back here of the chuck, and then we also have this over here. We have a high frequency actuator. If this can allow you to extend your frequency range, if you'd like to go above 300 hertz, you can go up to 20 kilohertz at room temperature with that high frequency actuator. Both the actuator and the heater are conveniently attached to the back of the chuck, so they are out of the way when you're working with larger samples. When using the dimension icon with AFM-nDMA, the workflow kind of goes as follows. The first step is pretty much the same as what you'd work with if you worked with an icon before. You just navigate to the area of interest using the icon motorized stage and the optics. Then you go ahead and you engage and scan with peak force QNM mechanical mapping. That gives you a fast, high-resolution mechanical property map and allows you to choose locations for doing your co-located nano-DMA measurements. And then finally, you basically can set up either an array of spectra or a map, say at a single frequency, or individual points, or a vector. Any of those are possible within Moroview. So how does the AFM compare to bulk DMA? Well, we compared our results on PDMS, and we found that we are getting excellent agreement with both the Heisotron nanoindenter, which is shown here in crosses, blue crosses in the center, and with the bulk DMA machine, which is the green lines, and this is storage modulus and loss modulus down below. The blue circles are AFM-nDMA measurements collected in Santa Barbara, and the orange triangles are collected on a different system with a different user in a different lab. So we're getting very consistent results, even without using any reference samples other than the sapphire that Dalia mentioned in order to calibrate the deflection sensitivity. And we also did extend the range, so you notice that the Heisotron and the DMA kind of end at around a couple hundred hertz, but we're able to go up to about 20 kilohertz by using the external actuator. So back to Dalia.
Okay, thanks, Bede. So now I'm going to show some data on an expanded set of samples. So again, the general concept here from the workflow that Bede just described is the ability to make localized viscoelastic measurements for heterogeneous samples. So first you would image with a conventional AFM technique like peak force QNM just to find an area of interest. Here we had a heterogeneous 4-component polymer blend. So we found a good area that had representative domains for each. Then we conducted an AFM-nDMA map at 100 hertz. So again, that's a pretty high frequency, But in order to image, you want to do this at high frequency. The low frequency image will just try everyone's patience. And so now you have an image at 100 hertz. This is the storage modulus image. And then you can actually point and frequency sweep. So point and shoot into different areas, into the different components, which is what we've done here, and collect a full frequency sweep of the viscoelastic moduli. So here we're showing the storage modulus as a function of frequency up to 200 hertz. We did not have the high frequency external actuator loaded here for this sample. And so now we can see the storage modulus as a function of frequency for these 4 components. So now you can add temperature as a variable to these frequency sweep measurements. Again, this is what is done a lot in the conventional DMA community. So here we had a different blend. We had a blend of polypropylene, that's the matrix, that's in the background, and then a domain of cyclic olefin copolymer here in the middle. And so we mapped now the storage modulus and loss tangent, again at 100 hertz, as a function of temperature, from room temperature all the way up to 175 degrees C. So what we see in the storage modulus maps is that the cyclic olefin copolymer at high temperature is much stiffer than the polypropylene. And so these actually diverge. Their storage moduli diverge as we increase the temperature. The loss tangent has a very different story. So the cyclic olefin copolymer has a lower loss tangent than the polypropylene at room temperature. But as these get heated and we approach the glass transition temperatures of these two materials and even pass through them, we can see that they become very close to each other. The loss tangent becomes very close, and then they actually invert. So now the loss tangent here for the COC is higher than that of the polypropylene matrix. And so down here you can see a plot of the storage modulus as a function of temperature. Here's the loss tangent as a function of temperature at a fixed frequency for the two materials, and you can see how here the storage moduli diverged and here the loss tangent crossed over. But again, being able to make these measurements as a function of temperature provides us with the ability to pinpoint these thermal and structural transitions that these viscoelastic moduli are known to do. Here's another example of trying to look at a quantitative comparison with bulk DMA, and this is focusing on loss tangent. Again, loss tangent is the most empirically useful parameter out of the 3. So this was looking at 2 different components. We had linear low density polyethylene and then an elastomer, which is a rubbery type of material. So in bright red is the bulk DMA values for the polyethylene. In dark blue are the bulk DMA values for the elastomer. Then orange are our AFM-nDMA values for polyethylene, and then light blue are the AFM-nDMA values for the elastomer. So we can see in the bulk DMA, we actually get a crossover for these loss tangent at a low frequency at about 1 hertz. At the AFM-nDMA, also we see a crossover. It comes actually at a little bit higher frequency, a little bit above 10 hertz. So we can see a little bit of discrepancy between the AFM-nDMA and the bulk DMA, but we can see here in terms of the absolute values, nice accuracy between our AFM-nDMA and the bulk values. If we now look at individually the storage and loss modulus data for these same materials. So up here we have the storage modulus, down here we have loss modulus. So focusing on the storage modulus, again, red is bulk DMA for linear low density polyethylene. The dark blue is the bulk DMA for the elastomer. This is the AFM-nDMA for polyethylene, and light blue is the AFM-nDMA for the elastomer. So we can see on storage modulus, there is excellent agreement for the elastomer between the bulk and the AFM-nDMA. For the stiffer material, where the tip is going to be penetrating a little bit less into the sample, our AFM-nDMA values are a little bit low, but within the error, still within 25% or so of our bulk values. And here we see similar trends for the loss modulus. Again, the elastomer, where it's soft, so the tip is penetrating more into the sample, getting better signal. We get very nice agreement on the loss modulus, and a little bit low at low frequency for the polyethylene, the stiffer material, and a little bit actually on the high end for the higher frequencies. Another example of, again, a more real-world sample, it's called a plastomer, where we looked at the loss tangent as a function of frequency and temperature now. So these dark blue dots that are connected, that is the bulk room temperature DMA data for the loss tangent of the plastomer. The light blue is the room temperature AFM-nDMA data. Again, it's a little bit low on this plastomer. And then what we did is we raised the temperature. So the orange points are the AFM-nDMA at 50 degrees C, and then the yellow points are the AFM-nDMA at 80 degrees C. And so we can see a plateauing of the loss tangent here as we raise the temperature, as this plastomer is approaching very close to its thermal transition. And finally, in terms of resolution, so again, for these well-controlled probes, they come in two flavors, either one with a 30 nanometer radius or one with a 125 nanometer radius. And so we had a blend here where we had these two blocks that were cryotomed together. We could look at the interface to probe the resolution of the probes, how well the measurement's doing. And we can see that in terms of measuring the interface on the 30 nanometer and the 125 nanometer, there actually wasn't a huge difference in resolution, despite the fact that we had very different tip sizes. And in fact, the 125 nanometer tip certainly also has better signal to noise. Again, not surprising. It's more contact area, more penetration into the sample. So, okay, and now back to Bede.
Great. Okay, I'm going to talk a little bit more about what happens when you vary the temperature. I mentioned earlier that rheologists need the storage and loss modulus at both a range of frequencies and at variable temperature for a complete analysis. This is to allow the use of time temperature superposition in order to generate a master curve. So what happens is if you can collect the frequency spectra at several different temperatures, you get little curves like these. So each spectra is shifted a little bit. And then what you can do is near the glass transition, raising the temperature is equivalent to lowering the frequency. So here we have some high temperature measurements down here, so they could be shifted over to the left in frequency, and the low temperature ones shift to the right in frequency. And what the rheologists want to do is they want to generate a master curve, so they get a huge range of frequency, and they know a lot about their sample and the behavior of their sample. Additionally, what they can do is they can look at all of the shift factors. In other words, how much did they have to move each of these little spectra. They can plot that up, and they can use either a WLF or an Arrhenius model to analyze how those curves shifted in order to figure out, say, an activation energy for the material. So what if we try this with AFM-nDMA? We need a bunch of spectra at different temperatures. So this is doing this on a fluorinated ethylene propylene sample. And we have in blue the storage modulus, and then in orange the loss tangent. We have the spectra. So the spectra are kind of these different colors of blue. And then we have different temperatures, right? So we have temperature on the x-axis here. And the behavior is pretty much what we expected from Dalia's earlier slide showing what you would expect for storage modulus and loss tangent as a function of temperature. And we're also getting the expected frequency dependence. In other words, the loss tangent is shifting to the right at lower frequencies. So so the question is then, how well does this match the bulk measurements? So here we have the bulk measurements in green and the AFM-nDMA measurements in blue. And we get a reasonably good match of both the glass transition temperature and the behavior around the glass transition. And once you've created this master curve, notice that you now have the behavior of the material over more than 20 decades of frequency. So from extremely low frequencies that would be unbearable even for a graduate student to very high frequencies as well. If we compare the Arrhenius fit, the activation energies actually come out really close also for both the bulk and the AFM. So that's very encouraging. Another variable temperature experiment demonstrates that the sample microstructure can affect the mechanical properties of the sample. In this case, the amorphous polyether ether ketone, or peak, has a sharp glass transition, but once it crystallizes, the glass transition disappears. So this is looking at the bulk DMA from Bruker here. If you increase the temperature, you see a very sharp peak in your loss tangent, or tan delta, and also your storage modulus drops at the same time. Right. Then what happens is the sample starts to crystallize, and that's indicated by this increase in the storage modulus. And that's without even actually reaching, you're not melting it. You're just giving the material more mobility by increasing the temperature. So, and then when you change the temperature back down to lower values again, now this peak is significantly reduced. And in fact, it would completely disappear if there were no amorphous peak available any longer. So there's a little bit of amorphous material still left in the sample. The AFM nano-DMA measurements agree very well with the bulk measurement. We see the same drop in modulus and the same increase in modulus, and we see the sharp peak on the up, and we do not see a sharp peak going down. But additionally, the AFM can provide correlated high-resolution structural information because it's an AFM, right? So we can do imaging. So at the early onset of the glass transition, at around 142, we start to see some crystallization actually near the surface and near defects in the material. That isn't enough to affect the bulk behavior much. But as you increase the temperature, now you start to see more and more crystallization. And when you hit about 170, you have this fine uniform structure that forms. And that structure does not change when the temperature is lowered back down to room temperature. So this is a known mechanical behavior, but it's interesting to directly observe the simultaneous morphological change in addition to the mechanical change in the sample. So in summary, the AFM is a natural tool for doing nanomechanical measurements, but traditional imaging modes are not really very well suited to doing studies of viscoelastic properties. And that's because of the nonlinearity of the measurement and the frequency mismatch when compared to bulk DMA. AFM-nDMA solves these issues by doing the measurements at the same frequencies and by doing the preload with a small perturbation in force. That gives us a linear measurement. And not all samples are as easy as a PDMS, but even the real-world samples that Dalia talked about have reasonable agreement with bulk DMA measurements. So we have this beautiful matching of the data with the PDMS, but we also have very good matching with the more important samples, which are the ones that our users are interested in, and everything looks good. Since the AFM-nDMA works at well-defined frequencies and temperatures, it is possible to generate master curves using the time-temperature superposition, as well as doing the Arrhenius or WLF analysis with the resulting shift factors. And then finally, AFM brings the possibility of doing the measurements with the resolution of better than 50 nanometers. And that really gives you the possibility of doing something you couldn't have done with a bulk DMA machine or Isotron, and that is to understand the influence of the microstructure on mechanical properties of materials. So with that, I would like to thank you, and please go ahead and submit your questions if you have not already done so into the chat window, and Thomas will help us to choose
yes,
first.
Yeah. Thank you very much, both Bede and Dalia, for this very interesting presentation today. And yes, as Bede mentioned, if you have questions, use that question dialog box and submit it. We actually have a lot of questions already. We'll do our best to cover many of them right now, and we will follow up with email if there's a question we don't cover now, so don't hesitate to submit it if it's anything you'd like to know further here. So let me have a quick look at the list here, and I'll go roughly sort of chronologically through the questions. Let me see here. Yeah, we had an early submission that was that asked to do more of a comparison where we look at the AFM techniques, the traditional ones, the nano-DMA now. Where do tapping mode based techniques fit in particular those where you excite several resonances, say bimodal tapping? How would you compare that to nano-DMA or other nanomechanics techniques? Bede, maybe you have a comment on that? Or is Dalia? Dalia, please go ahead. Dalia, let's start.
I'm happy to comment, but Bede, if you feel strongly, you can try and take that one. Nope. Okay. Yeah, so the multi-frequency methods that are tapping mode also have some serious constraint, or tapping mode based ones also have some serious constraints. First of all, because these multi-frequency techniques are very high frequency, right? So high order eigenmodes are by definition higher frequency than the fundamental. So you're going even further into a high frequency space. Usually they're in the megahertz regime, away from a low frequency space, which is really where you want to be, especially if you want to be able to compare with bulk rheological techniques. Second, you are constrained to operate at the frequency of the cantilever. You can't sweep. So you're constrained to whatever the fundamental mode is, which you don't have much control over, and then wherever its higher order modes are So you can, those are the only frequency you can measure at. Finally, these multi-frequency methods typically rely on Hertzian mechanics to derive any of their material properties. There's no adhesion in Hertzian mechanics, and so it's not bad for stiff samples, but for softer viscoelastic type materials, you really do need a model that incorporates adhesion to accurately model the tip sample interaction. So I'd say that's kind of a third challenge with those methods. I don't know, Bede, you want to add anything more? But
yeah, I'll add a couple things. One is, when you see loss tangent calculated using one of these methods, the models these multi-frequency methods are using, since they don't include adhesion, they have a tendency to incorporate adhesion into the measurement in unexpected ways. So, for example, loss tangent typically ends up being significantly higher, like factors of 2 or to 5 higher than what they should be, even with a time temperature translation to the right frequency. So there's definitely there's some issues with making a quantitative comparison that is a little more than just the frequency problem, which is definitely an issue as well.
Okay, thank you both for answering this. I think it was a good question that was submitted early on. And actually, from the same submitter, we have a number of questions about doing electrostatic and magnetic measurements. And so let me just say that with the nano-DMA, our focus is really not that, because in a sense, if you think about it, by going into contact and doing these very small amplitude motions in contact, we're really sort of isolating short-range mechanical interactions. We do have other methods for MFM and related measurements. Aside from lift mode, we can do some combinations with peak force tapping. And so maybe we'll cover those parts offline, as they're a bit separate from the main topic here. Let me see. And another person here submitted a question on nano-DMA, the range of samples. Have we looked at the soft end? Have we looked at biological materials so far?
That's I'll take that one. That's a very good question, and I think there is a lot of potential from very interesting experiments in that realm. However, doing the measurements in liquid adds some complexity to the measurement that we didn't want to take on in the initial release of this product. So we have not done much with extremely soft materials. We have done down to around in a couple of megapascals currently. We expect that this will work into the kilopascals if the adhesion is not too high, but maybe not down to 1 kilopascal. That is very difficult to avoid adhesion at that point.
Yeah, I guess we find that adhesion is an extremely important point, and as much as you try to avoid drastic adhesion effects from ripping out, you can keep refining this further and further. Even staying in contact, you can talk about a hysteresis effect there that is known in the indentation community. And so you get to these levels of refinement, and when materials get very soft, right, that contribution becomes larger. Actually, another question also submitted early on was about the time temperature dependence. So this time temperature superposition that may have been addressed partially, but here the question was, since the temperature dependence is an important part, do you expect effects from the tip as the mechanical properties of the tip will also change in principle with temperature? Any comment on that? So definitely there is a
a possibility for cantilevers to bend when the temperature changes, and that's an important thing to consider. And we've actually incorporated that into the development of this product in tuning the cantilevers to be appropriate for the measurement. So, for example, some of the softer cantilevers have a special, they're specially designed, we'll put it that way. However, the tip material modulus is not going to change, and the cantilever modulus is not going to change. So spring constant will remain pretty much constant, but again, the base deflection that will shift, and especially if you have a cantilever that is not optimized.
Yeah, and we have built in a sort of drift compensation into the softer levers in this case, right, where you want a very reflective lever, but also one that doesn't drift with temperature, and we did actually find a solution for that.
Mm-hmm.
Another question on what instruments this is available for. It's on the Dimension Icon and Icon XR, and at the moment, that's where this AFM nano-DMA mode is available. We had somebody else ask, will this video be available later? Yes, it will be. The video and audio will be available together with a slide set later. Here we have a question on, I think this is slide 12, slide 12 of Bede's slides. There was a question whether the E double prime was going to 0 or not. I believe it wasn't. I'm not sure if this was the E double prime of the PDMS, maybe, Bede. Is it slide 12? I didn't catch it at the time.
Let's see here. So E double prime is not going to 0, but it is fairly small. It's a few megapascals.
Yeah. Okay. Good. Yeah. That's what I. That's what I thought. Let me go a little bit further down the list. Bear with me for a moment here. Could you comment on matching frequencies and matching strains? There's a question on, since the strains will be different, is that a concern in the measurement, and wouldn't that affect the matching with the bulk?
So, typically the way the measurements are done, you want to, and this is true in the bulk DMA also. So if you're doing like you want to apply a preload, and then you want to find an amplitude that's big enough to give you some signal, but not too big so that you exceed the limit of the linear limit of the material. And so the same is true for AFM, but the idea there is that we want to stay linear, we want to avoid plastic deformation, we want to use small amplitudes, so one of the key considerations for AFM is how much preload can you apply before you start causing plastic deformation, and that is a key thing to consider.
Yeah, right. Thank you, Bede. Right, yeah, you do want to stay in the linear regime. The larger tip may make that easier than the smaller tip, but you may want to look as a function of preload or as a function of amplitude to ensure you're in the linear regime. Then you should be able to compare. Mm-hmm. Here a question on what's the thickness of the films that you can look at? Is there a lower limit where you start to see substrate effects?
We would expect that. We have not reduced the thickness of our samples down enough to see it yet. But yeah, I would expect that we would see substrate effects if we have a significant amount of deformation. the material, and we have a very thin sample. Most of the samples we're looking at right now are cryosections that are in the 100 to a few hundred nanometers in thickness or more. And so as long as our deformations are quite small, like 10 nanometers, which is not unusual for AFM, then we shouldn't have too much of a problem.
Yeah, and Bede, I would also just add to follow the general 10% substrate effect rule, right? That you want to just be deforming to less than 10% of your film thickness in this measurement, as with all measurements, to avoid the substrate effect.
Absolutely, and I mean that rule is a good rule of thumb. It's not always true, but it's a good starting point for sure.
Yeah. Thank you, Dalia. Yeah, it's very important, right, to have these, and so have a good idea where to start and how thin you can go. Where part of the attraction here is that you can go relatively thin compared to other techniques, compared to a larger scale, say indentation, right? That also in the third axis you can go smaller. We had another question on the calibration, where there was a concern with the calibration of the cantilever change. We offer these pre-calibrated cantilevers, and they are vibrometer pre-calibrated. If you now scan for an hour, would you expect the cantilever spring constant to change? I think the answer is no.
That's right. I mean, the thing that would change is what Dalia mentioned, which is tip contamination might happen, and but we do not expect the cantilever to change, spring constant to change in that time. But yeah, again, the tip can get contaminated, or if it's a very stiff sample, it's possible to have it damaged. However, these 30 and 125 nanometer tips are extremely robust, and really they don't get damaged on polymeric samples.
Yeah, thank you. Yeah. Thanks. Let's see. We had a question here on these reference segments. Bede, could you explain once more how you do the tracking contact radius, or how the reference segments work?
Sure. Basically, what you do is you put in. You want to have these reference segments kind of throughout your measurement, and what you do is you have one right before the retract curve and one at the very beginning of the measurement, and then you have a few throughout the in between the other frequencies. And so you measure the stiffness at each of the reference frequencies, and you assume that the storage modulus is constant throughout the script. So then by using this very simple relation, you can actually get the contact radius for each of those reference segments. And then you can interpolate between them to allow you to have a contact radius for each of the segments that are not reference segments.
Okay, thank you. Yeah. And another question about the TTS. Since you can do time temperature superposition, why can't you measure it at much different frequencies and then do a shift into the interesting range of frequencies?
Yeah, we've done that quite a few times, actually. In fact, the data that Dalia showed, where she compared peak force tapping with the DMA, essentially what was done there was that the DMA was shifted to cover into the 2 kilohertz range of frequency. However, that's one way, right? So you cannot actually go from and do the time temperature superposition in the other direction. So if I have a component in my sample, and I really want to understand exactly what's going on with that component, and it's small, really the only way to do it is by doing measurements at different temperatures and different frequencies for that one small component. The component probably or may not exist at the scale that is required for a bulk DMA measurement.
Thank you. Another question we had was about cantilever drag. This was somewhat targeted at measurements in liquid, but I think it may be an interesting one in general. Is there drag of cantilever that would in principle matter if you're making a very sensitive phase measurement in the nano-DMA, to be dragged through air or much more so through fluid?
Well, I think for the fluid case, I would suspect that there probably is a significant amount of drag there, and it might need to be considered. In air, we're talking about low enough frequencies and very small amplitudes. So we're talking about 1 nanometer amplitude at 100 hertz. I don't think there will be much drag there.
But we would expect it to be a small effect, especially at these conditions. We do also run the same script on a hard sample. I think right to basically calibrate the phase.
That's right. Yeah. So there is a comparison that is done to calibrate out the phase shift. So yeah, that actually might help solve the problem for fluids too. But again, we haven't explored that very much at this point.
Let's see. Working through the list here, another question on. How does this technique compare with force relaxation, with a sort of a DC creep test for measuring viscoelasticity? Can you comment on that?
There, in the literature, there are some papers that look at that. One of the nice things about this method is that when you do a creep relaxation measurement, there's a tendency to adjust the amount of time over which you do your fit based on an approximate time scale that you think things are happening in. That may work well if you have some initial idea of what that time scale is. But the nice thing about this approach is that it doesn't make any assumptions about what the time scale is other than the limits on the frequency range that you select. So I think it's a little bit easier to avoid subjective choices in your measurement conditions.
Another person asks here, he states that he missed the beginning, so he may have missed a part, but asks, how do you calibrate the either the E prime or the E double prime, or what reference sample would you use to calibrate the modulus?
So I guess I'm taking all of the questions, Dalia. I'm sorry about this, but
no, it's quite all right. It's these are operating principles questions that you can answer better than I do.
Well, okay. So the calibration goes as follows. What we do is we scan the box of probes, and the box has already the information of each cantilever. Essentially, it knows the tip radius of the probe and also the spring constant of the probe. So that's already there. We are missing the deflection sensitivity. So we engage on a hard sample like sapphire, and we do a ramp and find the deflection sensitivity from that. At that point, our system is calibrated for doing force measurements, but there is one additional calibration that's necessary because the system is very sensitive to phase shifts. We also do a calibration by running the same ramp script on a sapphire sample in order to find if there is any significant phase lags from the electronics or anything else in the system. And usually that'll correct another couple of degrees of phase shift. And that's it, basically. Everything else is, there's no sample that, or no need for a sample at a known modulus, for example.
Right, so we do use the hard sample, but we don't need to recalibrate the tip radius. We use the absolute value.
Yeah.
Another question here about, and this maybe gets into some of the finer points, really becoming more quantitative here. So you're doing this oscillation on the sample. You'll cause hysteretic adiabatic heating that will change the local temperature. Any comments on that, since energy density can be high under an AFM tip? Do we expect a significant temperature change? Would that have an effect?
I mean, so this is also something, this question asker is probably somebody that's pretty familiar with DMA, because it is also an issue for bulk DMA machines. And the issue is that essentially there can be frictional heating within the material when you start vibrating it. And that could cause a temperature shift in the measurement. With AFM, we have that. We also have we have a laser on our cantilever. The temperature is not completely uniform around the cantilever, so there is some uncertainty in the temperature of the sample where it's being interrogated. But so far, the measurements that we've done, it looks like we're within a couple of degrees of what we think we are.
Another question on the spatial resolution. You made some comments on spatial resolution, what we see empirically with these different size tips. What do you think sort of limits the spatial resolution? Is it strictly the contact area? It's the sensitivity of the measurement? Is it something else?
I mean, the contact area is definitely, so you have to preload, right? And if you want to get some signal, you need enough amplitude to do a measurement. That means your preload needs to be a bit larger than that amplitude. So you need to have the tip have a fair amount of load on it that causes some deformation. And so it's not just the tip radius is what I'm trying to get at. It is a combination of the preload and the tip radius that gives you a contact radius. And that will be kind of the starting point to the resolution. Of course, if you have, you have a strain field under the tip that's often bigger than the contact radius. And that's why when we did our comparison there, we looked at actually an interface that had different materials in it, and we looked at where it looked like the modulus was leveling off on those. So that's the source of our comment about the resolution. If you were to look for say at a block copolymer or something like that, I've seen significantly higher resolution images than that, but I can't tell you that they're not being influenced by the adjacent components in the material.
And Bede, I would just add that what you're saying really applies to most AFM-based methods. Right, it's really contact area, which is a function of the tip radius and how much you're deforming into the sample. So even when you have regular tapping mode imaging with conventional sharper probes, depending on how much that tip will sink into different materials, depending on their modulus, will affect ultimately the resolution as well. So it applies, I would say, even more broadly.
Yes, right, definitely. Yeah, thank you. Thanks, Dalia. Let's do one more. We're quite far over time already. One question was, can you compare or contrast nano-DMA with your fast force volume contact resonance? which will have some things in common and which also provides E double prime. What is the difference? What's different technologically and in terms of benefits?
Sure. Yeah. So the fast force volume contact resonance, it uses a different kind of actuator, which is designed to work at megahertz or at least hundreds of kilohertz frequencies. Typically what we do is we do a frequency sweep during the contact in force volume. And then we don't really care that much about exactly what the amplitude is as long as we can detect the contact resonant peak and what frequency it is at and what the Q of that peak is. That gives us what we need to do the calculation. With nano-DMA, when we're working with force volume and we're doing one of these single frequency maps, we're not looking for a peak. We're not sweeping frequency. We're working at a single frequency, and we have carefully calibrated the amplitude so that we know exactly how much amplitude and phase there is expected. And so the calculation is different. The other thing is that with contact resonance, there's a lot of things that are very difficult to calibrate in the calculation. For example, the tip height, the tip setback, the tip angle, those kinds of things all come into the calibration. And as a result, people typically use a reference sample with a known modulus in order to calibrate the contact resonance. That isn't necessary in the DMA case because the calculation is a lot simpler and a lot more things aren't resonating.
And Bede, I would also just add from a very practical point of view, the frequency space for the fast force volume contact resonance versus this AFM-nDMA is very different. So relating to, I think, one of the earlier questions, not only is contact resonance very high frequency because it's based on, the contact resonance is based on where the fundamental eigenmode peak position is, but it's also at a discrete frequency that you have very little control over. Whereas for the AFM-nDMA, part of the utility is the ability to frequency sweep in a rheologically relevant frequency space, which let's call, around 1 to 200 hertz. And that enables a very straightforward and facile comparison to a bulk DMA. With contact resonance, you have to start doing time temperature superposition on your bulk DMA in order to get up to the properties at the high frequency that the contact resonance measurement is making. But you don't have the ability to sweep either. You do have some choice because the cantilever has multiple eigenmodes, so you can sample a few discrete frequencies, but you certainly don't have the ability to sweep, and you definitely don't have the ability to sweep at a rheologically relevant low frequency regime.
Yeah, thank you very much, Dalia. Thanks for adding that. I think that's very important. Let's end it at this point. We're almost half an hour beyond our normal time slot. We do have a few additional questions, and we'll follow up with email on those. Thanks again to Dalia and Bede, and thanks to those attending for your interest. Please do take the quick survey at the end to help us make these the most useful webinars they can be really for you. And with that, hope to see you at our next installment. Thank you. Bye-bye.